Hi there. This is Mike Masuda, physics and astronomy adjunct professor over at Evergreen Valley College and adjunct faculty physics professor at Gavilan College in Gilroy. This is a short, hopefully short video, a tutorial for my students over at Gavilan College regarding adding two force vectors together. They've had some questions and issues in trying to determine and draw the force vectors, and so I figured to put together this video tutorial for them. So anyways, their setup over there is a little different from the one at Evergreen, but you get the same idea essentially. I drew this little drawing here. It's basically, this is the table that they're using, and it's a circular table, and in the center there's a ring, and to the ring there's attached three strings, okay? And the three strings are basically suspended over the edge by pulleys, and each of the pulleys here on this side and over here, there's a mass suspended, okay? And these masses are known, and the angle between these two strings here is also known, okay? The actual tabletop here has the degrees, the angles labeled, okay, up to 360 degrees. And then the third string over here is the tricky part, because this is the unknown mass that they need to figure out that needs to be suspended in order for this whole thing to be in equilibrium, such that all three masses produce forces that balance out. Okay, and so the ring should be sitting very nice in the middle here once the calculations are done and everything's sort of figured out. Okay, so anyways, so this is our setup over at Gavilan, and I wrote down some arbitrary values here. Okay, some example values to use for this particular lab write-up. Okay, each of the groups had different masses and different angles that they had to sort of work through to figure out the unknown. I also forgot to mention, these masses here are hung on these little hangers that are each 5 grams. Okay, and so they have to figure that in as well, then added to some of the complexity. Okay, anyway, so these are the masses, and we have mass 1 here is 150 grams, mass 2 is 200 grams, the angle between as 100 degrees between the two strings that are, holding the masses up. So these are this is an example essentially of what I gave them. Okay, and so what they have to do with this now is figure out what the forces are pulling on each of these two strings. Okay, and so let me go ahead and do some calculations here for this, and have a handy dandy calculator over here. They don't have to get something as fancy as this, but I'll have this off to the side. So essentially, the force due to mass 1, we have to actually add another 5 grams to this because of those hangers. Okay? And so this turns out to be 155 grams. This is 205 grams. Okay? Now we can't leave it as grams, because in order for it to work with the convention in the metric system, we have to convert it to kilograms so that we have our forces in newtons. And so we use the relationship weight is equal to mass times acceleration due to gravity. And for the masses, we have to convert this into kilograms. Okay, so 155 grams translates to 0.155 kilograms. That's for mass 1. And for the other one, excuse me, for the other one, it's going to be 0.205 kilograms. Okay, let's work this one through first. So it's 155 kilograms times 9.80 meters per second squared. That's g, the acceleration due to gravity. Okay, and we punch this into our calculator here, and we can get our numbers here very quickly. 1.155 times 9.80, and we get 1.519 newtons, and that's the unit of force. Okay, and so this is the weight. We'll call this weight 1. Okay, now for the other one, we use the other mass, which is 0.205 kilograms, which is 205 grams, multiplied by 9.80 meters per second squared. Okay, and so if we do the calculations for this one now, we get 0.205 times 9.8, and this turns out to be 2.009 newtons for this one. So this is weight number 2. Okay? So these are the two forces here associated with mass 1 and mass 2. Okay? Now that we have the numbers for these forces, okay, these are the forces here, weight 1 and weight 2. In class I call these forces, but you know, they are being pulled down by the mass, the acceleration due to gravity, those masses, and so we could consider them weights if need be. Okay? So what we do now is we have to put together this thing known as a free body diagram. Okay, the free body diagram consists of those arrows that are the representative forces of these two things, and the angle between the two, we'll have to draw these as well. Okay, and so in order to do that, let me go ahead and move this off to the side here and use a different sheet of paper. So just to remind ourselves now, weight 1, and I'll use shorthand here, was 1.519 newtons, and weight 2 was 2.009 newtons. Okay? So what we have to do now is draw appropriate arrows. Oh, by the way, the angle between the two. The two forces was 100 degrees. And so what we have to do now is choose an appropriate scale. Okay, so we choose a scale that works for the piece of paper, the size of the paper. Okay, if we chose something too small, like 1 newton is correspondingly 1 centimeter, then everything's going to be really, really tiny on the paper, and that's not going to work so well. Okay, if we choose something too big, then it's going to stretch out beyond the edges of the paper, and that's going to get kind of messy. Okay, so we have to choose something appropriate to the size of the paper. My recommendation for the purposes of today is to choose something that is something like this. 1 newton, okay, of force is equal to 5 centimeters on paper. Okay? That way when we draw it, it'll at least fit on the paper. Okay? So here's the deal. What we do now is multiply these two values here of 1.519 and 2.009 by 5 to scale them to the paper, and so we get our values in centimeters. Okay? So let's go ahead and do that. So we get 1.519 times 5. This gives us, let me pull this down here, draw an arrow here so that these are the vectors here. This will be 7.595 centimeters long. And the other one, which is 2.009, multiply that by 5, we get 10.045 centimeters. So these will be the corresponding lengths of each of those two forces. Okay? So now what we got to do is draw these arrows, okay, to the appropriate scale. And I have here a handy-dandy ruler, and we have things in centimeters here. So the first one is going to be 7.595 centimeters. I'm going to draw this way. And 7.595 is pretty close to 7.6, okay, centimeters. And so I will go ahead and draw this from this point here, okay, on the thing outwards to 7.6, okay. I remove the ruler and draw the arrowhead there to designate the direction of this, okay. Now this is weight 1, the one correspondingly to this first weight here, okay. And then weight 2 is going to be 10.045 centimeters long, but we have to draw this at an angle of 100 degrees to the first one. Okay? You have to remember to visualize this thing as a force going this way along that tabletop that was round. And so we have to draw one force this way, and the other force is going to be about 100 degrees away from that going in this direction. Okay? The unknown is going to be somewhere over here. Okay, that's going to balance out these two forces pulling on this on the center ring in these directions. So now we have to use a protractor for this. Okay, I'll go ahead and put this down, and I'll put this down here. And oh, wait a minute. You want to make sure. You got to make sure of this. I just bought this protractor. You notice where the zeros are on this thing. okay, and the 180s. So what you have to do is line this up with the center dot here. Do you guys see that? So the center dot here is where the center of this should be, like so. I was originally going to do it here, but that's not going to work. Okay, we have to line this up so that the line lines up with this whole system here, and that looks like it's pretty good there. All right, move it over a little bit. And so this, this is the hard part here. So we can see that the center of here is where the beginning of the line is for the arrow. Okay, and this particular one has this handy-dandy little line up thing to draw a straight line. And so I will line this up with 100 degrees here, like so. Now remember, anything beyond 90 degrees is going to be greater than 90 degrees. Okay? And so if you're measuring from here outwards like this, be mindful that you're going to be going 10, 20, 30 this way, not 180, 170, 160. Okay? Those are the wrong measurements. Starting from here, that's 0. This is 10, this is 20, this is 30, and so on. 90 degrees should be exactly perpendicular to the line that you first drew. Okay? 100 should be a little bit larger. And so we'll go ahead and draw this out this way, like so. For the ones that don't have this little line, you'll have to put a little dot to indicate where it is. Okay? And once you remove this, this will give you a guide to where the angle is. Okay, so now this angle here is 100 degrees, but we now have to figure out how long to draw the second arrow. We said it was 10.045 centimeters, so about 10.0. Okay, that'll probably work just as well. And so we'll have to line this up over here. And pardon me, I have to do turn this a little bit. So we line it up along that line. We draw the line out this way to the edge of the ruler there. Okay? And so now we have this line here that is correspondingly appropriate for weight number 2. Okay? And we said that this angle here is 100 degrees. Okay so far? Now, this text here is probably going to get in the way. All right? So now what we got to do is add these forces together. And it's usually the beginners of the class that tend to mistakenly say, okay, well, this force is going this way, this force is going this way. The line's going to be going from here to here like that, and that will be the total force between these two. Not true. Okay, so what we have to do is think about how these things are being pulled. Okay, conceptually, they start here, and there's 2 ropes pulling it outwards this way. Okay? And so we have to think intuitively that the force has to go out this way somehow if you combine these 2 forces. If you were standing here and 2 people are pulling on you by ropes, you're going to go this way. Okay, so that's the idea. You have to think about this in terms of physics, that this is the direction that you should assume the diagonal to be for these 2 forces here. Okay, the addition of these 2 forces. It's not going to go this way. There's no force that's going to pull you this way when there's 2 ropes pulling you outwards like this. Okay, think of it in terms of that. Anyways, let me go ahead and continue on here. So we said that this is 100 degrees here, and what we have to do now is add these 2 forces together, tip to tail. And that means you have to go from origin to destination, and then origin to destination for the next one. And so essentially you line up the arrows so that they are tip to tail, tip to tail, tip to tail, and so on. Okay? There are only 2 here, so it will be relatively easy to do so. Okay? Now luckily for me, this protractor already has the 100 degree already, set up. And so what I could do now is line this up again as I did before. Like that. And then draw the line that will appropriately be for the 100 degree thing. And so as you can see, this guide line here and this arrow here, they are perpendicular to each other. Okay? Now, there are other ways to do this, of course. You don't have to use a protractor. As I found out yesterday, I went to an art store, okay, and they may carry these at Walgreens or CVS, but you can get something that looks like this. Okay? It's a rolling parallel ruler. And essentially what this does is if you use this to, actually let me just go ahead and take it out of the package here. If you use this to draw the lines, like so, or like this, okay? You draw the line, and then all you need to do is roll it over to this side over here, and it will, or at least it should, in theory, be the same direction. Okay, this one may not be as, well, maybe. See, it lines up very nicely with the other line. Okay, and so you don't have to use the protractor for, you know, drawing the second line here. You can get this thing called a rolling parallel ruler. Okay. Anyways, they do cost more. Protractor is you know, probably a few dollars cheaper. So it's up to you what you want to do with that. Okay. Anyways, coming back to this, we're over here now, and we need to draw one that is appropriate length. Okay. So we said that this one is about 10 centimeters long here, and so we'll go ahead and do the same thing over here. We'll line this up over here like so. Let me do it this way. So this point here is at 10 centimeters. And I line it up with the line that I drew as the guideline, and I go up like this. Okay? And it looks like it overlapped a little bit, so let me go ahead and erase this thing. Okay? We did say that 1 Newton is equal to 5 centimeters. My apologies for the camera shaking. 1 Newton is equal to 5 centimeters. Okay? So now this arrow and this arrow, they are the same vector. Okay? I just move this one over here so that I can go tip to tail and then tip to tail here as well. Okay? So now what I got to do is draw the addition of W1 and W2, the addition of those two forces. And what I'm going to do is draw it this way. Okay? From the origin to where it ends up over here. Okay? Like that. And meanwhile, I could probably do the same thing here. Measure the length of this thing. Okay, so this is going to be about, looks like it's about 11.4 centimeters. Okay, so 11.4 centimeters. This is the addition of W1 and W2, the two forces that we had. Okay, the length of this thing is 11.4 centimeters. 11.4 centimeters. What we have to do now is use the scale, okay, that we had up here, and we have to scale it back. And so we take 11.4 and divide by 5 now. And we get 2.28 newtons. Okay? So 2.28 newtons is the total force, okay, of W1 and W2. So this force here and this force here, as they're pulling on that ring, in these two directions, it's going to feel a force, a combined force of these two things, going this way of 2.28 newtons. And that's what we just did there. Okay? Now, we could say we're done with adding the two vectors together, but because Gavilan has the problem of converting this to mass, we have to take a few more steps here. Okay? 2.28 newtons. So what we have to do now is figure out what mass that is. And so what we do is rearrange Newton's second law, this F equals ma, or weight is equal to mass times acceleration due to gravity, in this case, for mass. So we move the g, we divide both sides by g. Okay, so mass is equal to weight divided by the acceleration due to gravity. And so 2.28 newtons, what we figured out, divided by 9.80 meters per second squared. Okay, so we do that, 2.28 divided by 9.80, and this gives us 0.232, so we can round this to 0.233 kilograms. Okay, so this is the mass that needs to be hung on that setup that we had before. So over here, the unknown mass now is known to be, what do we say? 0.233 kilograms. We figured it out. Okay? We're not done yet, though. Okay? Not quite done yet, because that third hanger also has a 5-gram hanging, system there. Okay? Some place to hang the masses. That thing is also, the hanger is also 5 grams. So what we have to do now is convert this to grams. So this is going to be 233 grams. Okay? And we have to subtract off 5 from this for the hanger. Okay, so 233, I could probably do this in my head, but we end up with, without the hanger, it's going to be 228 grams. Okay, so that is the mass that we need to hang on that side over there for it to sort of balance out everything. Okay, along with the 5 gram hanger that's already there. Now, the angle at which to put the third thing, okay, that's something we need to figure out, okay, because these two forces add up to this, okay. So now what we have to do is grab the protractor one more time and measure the angle that this thing makes. And so we put this in the middle again, like so, and line it up with the first line here, the first force. And I'll just move this over like this until it lines up. And it looks like it's at 10, 20, 30, 40, 50, 59 degrees. And so this angle here is 59 degrees. Okay? Are we done? Almost. This is the force of these two pulling on the ring. In order to get the force that will counteract these things so that the ring doesn't fall off the table, it has to be pulled this way. 180 degrees opposite to these two forces. Okay? So opposite to this, we just have to add 180 degrees to this. Okay? So 180 plus 59 degrees gives us 239 degrees. And so this angle here, starting from 0, this is at 0 here, okay? W1 is at 0 degrees, by the way. So we have to go from here all the way around to this point here like that. This angle, okay, for the third weight, okay, which we found out to be up here, 2.28 newtons. 2.28 newtons is at an angle of, what did I say? 239 degrees. 239 degrees. Okay? So, and the mass associated with this, okay, we said is 228 grams. Okay? Plus the 5 gram hanger. So that's the answer. Okay? So, hopefully, this video is going to be probably more than one segment long, because it's over 22 minutes, okay, at this point. So I will post this thing up in segments, part 1, part 2, and part 3, so that we have all the parts together, so you guys can watch this, okay? Again, this is Mike Masuda for Gavilan and Evergreen College in San Jose area, Gilroy area, and thanks for watching.